Yes, thank you. Good morning. So I would like to present in this talk a few results from an ongoing project at IEP in Paris, where we try to model in details the emission expected from internal shocks in gamma ray bursts from the optical to gamma rays. So this is done in collaboration with June3 Part3, Guillaume Bibus and Robert Moshkovich. So a few words about internal shocks, but we have already heard many things about them. It seems clear that emission from gamma ray bursts comes from highly relativistic outflow, but what is still not clear is the mechanism at work to extract the energy of the outflow and convert it into radiation. And there are several possible models. Some of them will be discussed by others during this session. And here I will really focus on internal shocks. So, of course, the idea is that due to the kind of initial event which is associated to gamma ray bursts, it's very likely that there will be some variability during the relativistic ejection phase, and then you will have some variability in the initial Lorentz factor distribution in the outflow, and then it's very natural to expect that some shock wave will form in the outflow and propagate. And if this shock wave can accelerate particles, then a reasonably high fraction of the internal energy which is produced by this shock could be radiated. Of course, a nice property of this model is that it can easily explain the high variability of the light curve and the typical time scales that are found. I will show you, and also Jelika in the next talk, that it can also reasonably well explain the temporal and spectral evolution which is found in gamma ray burst light curves. There are, of course, some problems which are well known for this model. I think the main one is relatively low efficiency. Some other problems, it has been claimed in the past that maybe the pulse, the temporal shape of pulses was not in agreement with what is observed, but it was usually estimated assuming that internal shocks are instantaneous collisions that immediately release the radiation, and then the pulse shape is only due to the spreading of arrival time of photons due to the curvature of the emitting surface, the so-called high latitude emission. But if you think of internal shocks more as really shock waves propagating within an outflow, you have an additional time scale which is related to the time needed for this shock wave to propagate, and then you can have more complex pulse shapes which are more in agreement with what is observed. And of course, one problem is if the ejecta is still highly magnetized at the place where gamma rays are produced, then maybe it's not possible to have these internal shocks. They will be suppressed due to the strong magnetization. Okay, so we have tried to develop a model to compute in a detailed way the emission from these internal shocks in gamma ray bursts. So I won't say too much because Jelika will describe this model in her talk. The idea is to try to find a good compromise to treat in a reasonably accurate way both the dynamics, so the propagation of the shock waves, and the radiation. Briefly, so we have a code which is not really, it's not a real hydro code, but it's more shell approximation for the dynamics. For the microphysics, as usual, we do some parametrization. What is important is that for the electron distribution which is produced by the shock, we have two parameters. I mean, in addition to the slope, the fraction of the energy which goes in the non-thermal population and the fraction of electrons that goes in this population. We do not necessarily assume that all electrons are accelerating. So then with this code, from an initial state, here it's a very simple situation where in the outflow the Lorentz factor increased from 100 to 400, so you have mainly two parts in the outflow, and it will produce a single pulse in the light curve. So from such a situation, we can compute the light curve in different channels and also the spectrum at different times. So one first question that one can ask is, what is the dominant process in the, let's say, in the Batty range, the keV, MeV range? Do we observe gamma rays which are directly produced by synchrotron radiation from the electrons, or does this synchrotron radiation peak at lower energy, and do we observe the results of inverse Compton scatterings? What we find is that if we explore the parameter space of internal shocks, of course both possibilities can occur, but corresponds to different assumptions regarding the microphysics. So first, the case where gamma rays are produced directly by synchrotron is usually more efficient. I speak in terms of what is the fraction of the total radiated energy which is in the Batty range. But on the other hand, to produce directly gamma rays by synchrotron radiation, you need to have a very high Lorentz factor for electrons. So usually it necessitates that only that a reasonable fraction of the available energy is injected preferentially in a low fraction of the electrons, so that it makes more energy per electron and you can reach higher Lorentz factor. So of course it's a strong constraint on microphysics, but if you assume that, then you can easily get the synchrotron radiation in the right range, and you can get something reasonable for various values of the magnetic field, but depending on this value, you will have very different signature at high energy, as I will show you. On the other hand, if all electrons are accelerated, and so typical electron Lorentz factor are more moderate, then the synchrotron emission usually will peak at lower energy, and this is inverse Compton scattering that will produce gamma rays. In this case, I would say that the main problem is that it requires some fine-tuning to have most of the energy in the inverse Compton peak in the Batty range. You can, I mean, for most parameters, either your synchrotron component is dominant at low energy, and you would have something which is more a strong optical or UV burst, or you will put most of the energy in a second inverse Compton peak at higher energy. That's also been discussed recently by Piran Sarin. Of course, the broad spectral range offered by Fermi is a good way to test what seems to be preferred by nature between these different possibilities. And I will first show you the effect on the spectrum. So the idea here is that I take a typical collision somewhere in the outflow, and I fix the microphysics parameters. So here it's a case where only 1% of electrons are accelerated, and I vary the Lorentz factor of the outflow, and I adjust the other properties of the outflow, such as, for instance, the kinetic energy injection rate, so that I maintain the same observed properties, the gamma refluence, the peak energy. And you see that, of course, it's highly degenerate if you just have the information in the Batty range here. But in the high energy, you get something rather different, especially you have this cutoff due to gamma-gamma annihilation. And so there is a hope that you could, for instance, measure the Lorentz factor and, in addition, know the typical properties in the outflow. But remember that there is a degeneracy, because here I had to assume some microphysics parameters. Note that in this case, as the epsilon b is high, the efficiency of inverse Compton is very low, and you see no additional component in the lat range. So if I'm doing exactly the same thing, but now I have just reduced epsilon b so that inverse Compton emission is more efficient, you see I don't get a very strong emission, because still, as the Lorentz factor of electrons is high, Klein-Nischina limitations are important, but I have something which is different. So hopefully this degeneracy with microphysics parameters could be solved with a good spectrum at high energy. If now I'm doing the same for a case where all electrons are accelerated, so zeta is 1 here, and so now the gamma ray emission is due to inverse Compton scatterings, then you see that you have something which is really completely different and which is probably already excluded by Fermi data. One word about the measurement of the Lorentz factor from the cutoff energy. So here I have measured the cutoff energy in all the cases I have just shown you and plotted them as a function of the Lorentz factor of the flow. I have plotted the usual analytical estimate that is used to measure the Lorentz factor. You see that when synchrotron is dominant, it works quite well, but when if it was inverse Compton, it was a dominant process, and you have to be very careful because sometimes the cutoff is due to Klein-Lichtenstein limitation and not to gamma-gamma, and then you don't measure correctly. Of course, the spectrum is not the only available observation. You can also use the temporal evolution combined to the spectrum to learn something. So again, here I show a case where only a fraction of electrons are accelerated, so that's synchrotron radiation peak in gamma rays, and here a case with a high epsilon b. So you see that more or less in the LAT and in the GBM, you have something which is very similar. It's only above 1 GeV that you have a weak inverse Compton component that appears at a later time and make the duration of the burst a little longer at high energy. This effect becomes much stronger if you reduce epsilon b, which favors inverse Compton. And you see that now it's even possible that the inverse Compton component becomes dominant above 1 GeV, and then it would delay the peak of this component, the time of the peak of this component, compared to the emission in GBM or in the LAT, let's say below 1 GeV. Sorry, I skipped that. In the case where the whole gamma ray emission is due to inverse Compton, then such an evolution is not observed. I mean, the temporal evolution is more or less the same in all channels. So again, it's not the favored case by Fermi data. Okay, so now we have some observations. So we can try to see if already we can learn something in this framework. So as it has been told in the previous talk, the first bright GRB detected by the LAT is quite challenging because it has a huge isotropic equivalent energy, a very large Lorentz factor, very high peak, so it's not very easy to model, and unfortunately I won't be able to already show you something which would be a real detailed modeling of it. We are working on that. But the idea, compared to what I have just shown you, would be that we would try to explain most of the emission by a synchrotron component, and to explain the fact that at high energy the emission seems to start with a certain delay by the emergence of this inverse Compton component. Of course, it won't explain the long-lasting emission for 1,000 seconds. So it should have to be something different in this case. Of course, if the fact that we don't see a very strong inverse Compton component in the LAT favors this synchrotron scenario, and then it seems to imply that you have a low fraction of electrons which are accelerated and a low epsilon b. So then there are some possible consequences that have already been mentioned in Spikovsky's talk. The fact that you still have a population of thermal electrons that could also contribute to the radiation. So we have tried to briefly check if by chance it could contribute to the prompt optical emission. So very briefly, because time is running, what we find is that in principle, you could have a bright optical emission associated to this thermal population, except that once you take into account synchrotron self-absorption, you usually completely kill this emission. So it seems unlikely that it could explain, for instance, the prompt optical emission which is found in the naked eye burst. So just to finish, a few words about the naked eye burst. So there are several possibilities to explain the prompt optical emission in the framework of internal shocks. It has also these several possibilities are also discussed in this paper. So one possibility would be to say, okay, optical is from synchrotron and gamma arrays are from inverse Compton. The problem is that this is what was suggested, for instance, in the discovery paper. The problem is that then you have a big problem with energetics because you expect to have a very bright component in the lat range, and such bright components seem to not be observed by Fermi. Then there is a second scenario that I have just described. Non-thermal electrons produce gamma rays, and a thermal population produce optical. Then you have, but still everything is produced at the same radius. Then you have problems to avoid self-absorption. And so the scenario on which we are currently working would be a third possibility where you have a lot of variability initially in the outflow, and then a collection of internal shocks occurring at different radius with different relative velocities, and some of them will produce gamma rays, some of them will produce optical. So an example here, so I have taken a flow where the Lorentz factor is changing randomly between 200 and 800 for 25 seconds with a typical variability time scale of 0.5 seconds. And here you have the radius of all the collisions as a function of the time in the observer frame, with a color code for the typical epoch of the emission produced by each collision. So you see that you have late time collisions, well, not late time, collisions at large radius that peak at low energy and could produce the optical. And then you get light curves like this one, for instance, it is the same example, where you are if the very variable gamma ray light curve and the corresponding optical emission. You see that as this emission occurs at larger radius, you are closer to the slow cooling regime, so the variability is not so high. It lasts longer. It does not start much later than the gamma ray emission, which seems to be observed in the naked eye burst. But of course, it's a random realization. If I just change the distribution with the same assumption, I can sometimes have very different light curves, and even extreme cases like this one, where the collisions have occurred in such a way that it's only at the end that you have late internal shocks producing optical emission. So you could expect to have some delay like that. Okay, and this is my summary. Thank you very much.
Thank you. We have time for a couple of questions. Also, do you consider geometrical effects in your simulation? How that emission effects?
So yes, so I mean, Jessica will describe that. But once we have the dynamics simulation, so we know the evolution of the radius as a function of time for every shock wave and the condition in the shock region. And so we compute locally in the co-moving frame of the shock region the emission, and then to produce a synthetic burst, we integrate over equal or average time surfaces, so we take into account this effect. And this is why, for instance, even here, the last result I have shown was obtained with a poor discretization of the outflow, a small number of shells, but still we don't have, you see that even when you have just one collision, you get a nice profile like that, which is limited by this high definition.
So not every burst appears to be so optically bright.
Well,
special conditions to produce this?
Yeah, I mean, first, more variable bursts should favor optical emission because you will, I mean, it will favor a reorganization of the flow with still different parts which have not exactly the same Lorentz factor and that can collide later and produce the optical. So it could be somehow related to the variability. And also this burst is quite bright, so of course the total energy comes. And I mean, if I'm doing a lot of realization of a random initial distribution of the Lorentz factor, I can have really very different result at the end. I mean, so it depends really how your flow is reorganizing through internal shock. So I will not. And also I should mention that here the optical emission is very close to the break due to self-absorption. So if you change just a little the parameter, you can be much more self-absorbed or not self-absorbed at all. So I mean, you could expect some diversity due to that too.
Last question.
How important are secondary collisions of those shells in your model? And to which extent do you model this, the fact that after binary collisions, initial binary collisions, the shells will have, well, not the initial shape, but they will be different?
Yeah, so it's not taken into account because it's not an hydro code. So the point is that in the past, made a comparison between this shell model and the real relativistic hydrodynamical simulation, and we still had a relatively acceptable agreement even for the second generation of collision. But I agree that the agreement was not as good as for the third generation. So it could affect the results, but it's difficult to take that into account properly.
Okay, thank you then. And we will continue with internal shocks from Gamma bursts, and the next speaker is David Boschniak.
So I'm going to present the model that we have developed at TFA and that Frederick has mentioned for the calculation of the prompt gamma burst emission. And I'm going to show some temporal and spectral properties of gamma burst. So in the internal shock scenario, what we have that the initial inhomogeneities of the Lorentz factor lead to the creation of the shock waves that propagate within the ultra-elastic flow. So these shock waves dissipate their kinetic energy and accelerate the population of relativistic electrons. So as the acceleration of particles is accompanied with the radiative processes that are coupled to each other, so in order to follow the spectrum that is emerging from such a system, what we do is that we develop the code that follows the dynamics of the internal shocks. and we performed a detailed calculation of the radiative processes that are occurring in the shock medium. So how does it look like? So this is the first part of our model. So what we do is that we model the ultrarelativistic flow as with varying Lorentz factor as a succession of layers that are emitted. So in this example, every 2 milliseconds with varying Lorentz factor. So the more slower part is emitted firstly, so the more rapid parts, they catch up progressively with the slower part, and in every collision the merged shell is created. So what we do is that we follow the evolution of such a system until all the Lorentz factors within the flow are ordered. So that the Lorentz factors are decreasing from the front to the back part of the wind. So for every collision that occurs during the wind evolution, what we do is that we calculate we estimate, we calculate the parameters that are describing the physical conditions in the shocked medium. So shown here how does the Lorentz factor of the shocked region evolves the electron Lorentz factor and the magnetic field with the evolution of the Lorentz factor within the outflow. In this plot here, I'm plotted also some other quantities like radius and the so dissipated energy in every collision. So what we see here is that every plot, every curve here has 2 branches that correspond to the shocks that are propagating forward and backwards within the flow. So dissipated energy is distributed between protons, electrons, and magnetic field. So the common assumption is that the electrons are accelerated in parallel distribution. An important assumption that we do in our model is that in order to have the synchrotron, so the peak of the emission in the Patsy regime being due to the synchrotron photons, what we need to assume is that only a fraction of electrons are accelerated efficiently to relativistic velocities. Now, once that the dissipation of energy has finished, so the merged shells, they expand and cool. So we calculate in the radiative processes that are occurring in the shocked medium for every collision that has occurred during the wind evolution. So the calculation is done in Kamuic frame, and it starts immediately after the collision, and it is done on the time scale Tx. So this is the adiabatic time scale. The electrons cool on the typical time scale T-rad. So in order to have high radiative efficiency, we want to have this time scale much lower than the adiabatic expansion time scale. So what we have is that electron photon distributions are evolving strongly with time. The present version of the code follows the time evolution of the electron and photon densities, including the following processes. So adiabatic cooling, synchrotron emission, inverse Compton scatterings, synchrotron self-absorption, and photon-photon annihilation. So what we do is that we solve these 2 equations for the evolution of electrons and photons. Now, in order to so I've shown here how is the electron newly created photon distributions, how they are evolving in time. So this is the initial parallel distribution of electrons, and this is how the photon spectrum evolves in time. So the final, these are the calculations that correspond to only one shell. So the final spectrum that is emerging from this shell is the one that corresponds to the time Tx. So in this example here, we have peak is due to the synchrotron emission, but we have also the peak due to the inverse Compton scatterings, and the high energy part of the spectrum is attenuated due to the photon-photon annihilation. Now, in order to, this calculation is done for at all the times along the propagation of each shock wave. So in order to produce the observed light curves in spectra, what we do is that we take into account the contributions from all the collisions that occur during the wind evolution. The observed spectra and light curves are computed from the Kamuic emission by integration over equal arrival time surfaces. So we account for relativistic effects for the curvature of the emitting surface and the cosmological effect. So I've shown here how is the instantaneous spectrum evolving. So this is the light curve that corresponds to the, so it is done in the, it's calculated in 50 to 300 kV, so it corresponds to like second and third Batzy energy channels put together. So I've shown here how the inverse content component in this case evolves during the over the duration of the pulse. So this is an example of the synthetic burst that we can produce. So these are the light curves in different energy bands. This is the time-integrated spectrum. So I've shown what happens as we include different emission processes. So what happens if we include only synchrotron emission, then when we add also inverse content, and the final spectrum that you should look at is the shown in the red line, so where we have also photon annihilation and self-absorption included. So as Frederick has mentioned, so there are the two important cases that we'd like to look at. So these are both cases in which the peak of the emission is due to the synchrotron emission. They are different in that it has, in one case we have the inverse content component at high energies is negligible, while in the other case the lower magnetic fields are involved in the shocked region. We have lower magnetic fields in the shocked region, so we have stronger inverse content component. So I'm going to show what are the light curve and spectral properties for these two cases. First, if we look at the light curves, the low energy bands, corresponding to the 4 Batzy channels, the light curves in both cases look similar because in both cases the main contribution to the emission comes from the synchrotron radiation. So I've shown here what we obtained for light curve. It's exactly what was observed for the Batzy gamma burst. So that the energy emission corresponding to low energy channels is delayed with respect to high energy channels, and that the pulses are broader in low energy channels. However, the differences come when we look at the high energy channels. So I've shown here, so in red we have the synchrotron, the contribution of the synchrotron emission, blue is the contribution of inverse content scatterings, and in black I've shown the total light curve. I'm going to explain what's going on here on this example here, so because here I have stronger inverse content component. So what is important here is that as long as we have only one emission process that is responsible for the that is contributing to the light curve, then we have a simple evolution. But as soon as we have synchrotron and inverse content components, then we can have different sorts of behavior, different kinds of behavior. So if you look what happens in the parameters of the internal shocks, we see the following. So I've plotted here Lorentz factor of the electrons, the dynamical time scale, and the synchrotron time scale, how it evolves over the pulse duration. So what we see here, that in this case we are going to have first like a strong inverse content emission. So what happens is that due to the distribution of the Lorentz factor, initial distribution of the Lorentz factor that we have adopted, we have initial weak shock, so dissipated energy is low. We have moderate Lorentz factors of the electrons, so we have large synchrotron time scales. At this early time, the radii are small, so the dynamical time scale is also small. So the two time scales are going to be comparable. So what we have is that the large fraction of the shocked region is occupied with the relativistic electrons. So we are going to have a strong efficiency of the inverse content component. As we go further in time, what we get is that, so this is these times correspond to the peak of the synchrotron emission. So what we have here is that the shock becomes stronger. We have highest electron Lorentz factors, so the synchrotron time scale is lower. the expansion timescale is increasing with radii. So we have in this region here low efficiency of inverse Compton component, and the dominant contributions come from the synchrotron emission. What is important to see, to notice here is that due to these two, as we have two emission processes that are contributing to our light curve, we are going to have the opposite tendency of what was noted for what was observed for the lower energy channels, like in BATC energy band. Now, during the tail of the light curve, what we have is that the magnetic field is decreasing with radius. So mostly because of that, the synchrotron timescale is increasing. And again, we are going to have comparable the two timescales, so the dynamical and the synchrotron timescale. So we are going to have again increased efficiency of inverse Compton components. So it is going to be dominant in the GeV energy band. So I've summarized here our results. So, as long as we have mainly synchrotron component contributing to, this is the position of the pulse maximum, and this is the width of the pulse in different energy bands. So these are the 4 BATC energy channels. So as long as we have one emission processes that is responsible for the emission, we are going to have the observed behavior that is observed for the BATC gamma ray burst. But when we are going to have the strong inverse Compton component contribution, then we expect a delay in the high energy light curves. So I'm going to say now a few words about what's going on with the spectra in these two examples that I've shown. So I'm not fitting in order to describe our spectra, I'm not fitting the band model as we're examining the spectra on the broad energy range. Also, as I've shown, we allow for the possibility that during the evolution of the pulse we have strong inverse Compton components. So we cannot accommodate that. I mean, we cannot describe it with a single parallel at high energies. So what I do is that I calculate the slopes along the for every energy channel of the spectrum, and identify parallel spectral components, so where the slope of the spectrum is not varying within 0.1 on at least 1 decade of energy. So I describe our spectrum with the several parallels and the 2 peak energies that are corresponding to peaks of the synchrotron and inverse Compton emission. So I call this slope here, so I have alpha and beta that are identical, like in the discrete band model, and I have something that I call alpha high energy, so this is the slope here of the high energy component. So I'm going to show now how are these peak energies of both components evolving in 2 examples. So I've shown here also the ratio of the inverse Compton to synchrotron component. So as soon as this ratio becomes larger than 1, then the peak of the total spectrum is due to the inverse Compton component. Now what is interesting here is the following. So I've calculated the slopes in the way I described, and when I have the emission due to the synchrotron, the peak due to the synchrotron emission and the inverse Compton component is almost negligible, then I obtain what is well known for the fast cooling synchrotron spectrum. However, here when I have present inverse Compton component, what we see is that the low energy portion of the spectrum is becoming harder. So it is approaching to the limit that is observed for most of the BATC gamma ray bursts. Now, what is going on here can be understood if we look at this diagram here. So this is, I've plotted here ratio of the inverse Compton to synchrotron component versus the factor that tells me whether we are in the scatterings occur in Thomson or Klein-Machine regime. So if we look at the traits, the path that the burst does during the pulse evolution, we see that when we have the negligible inverse Compton component, then most of the scatterings occur in Klein-Machine regime. For this burst here, what we have is that when inverse Compton, the low energy part of the spectrum becomes harder when inverse Compton cooling is still present, even though the scatterings occur in Klein-Shin regime. However, saying that all of the observed gamma bursts occur in this transition region between Klein-Shin and Thompson regime should impose very strong constraints on the gamma burst parameters. So, we are still examining what is going on here. I'm going to skip this, and I'm just going to show, this is the last slide. So I've shown here how is in this case where I have scatterings occurring in Klein-Shin regime and I still have moderate inverse Compton component, what is going on with the spectrum with respect to the analytical estimates that involve the time averaged electron distribution. So we see here that the spectrum, low energy portion of the spectrum is becoming harder as the cooling rate of the electrons is different. So these are my conclusions.
Thank you. Questions? Can I ask you, so we assume always Pauli injection of electrons, yeah?
Yeah.
So, I mean, if you assume something else, because now you have very broad spectra.
We'd assume like peak distribution for, yeah, we did not try that, but
and you allow cooling, right? So you take all the energy and give them to the electrons, because you still get the problem with the cooling, right? So I mean, the spectra are very soft that you get because you have cooling. Because I mean, if you just inject electrons and let them cool, you will get cooling spectra.
Yeah.
So we should contradict most of the gamma reversed.
But the point is that what we assume is that we accelerate only a fraction of the electrons. So this is.
So they will cool anyway. So.
But what is the? I mean, sorry, I don't understand what is the problem.
I mean, because you get the cooling spectrum, so these are too soft. That's the problem.
You mean like we obtain like -1.5?
Well, 1.5 exactly.
What I'm saying is that inverse Compton component.
So we play with that, you can sort of get slightly harder this I also understand. But
Yeah.
I mean, you have spectra which have indexes zero photon index.
No, what I've shown here is that we can get close to -1,
Yeah.
so going from -1.5 to -1.
Yeah.
But yeah, we did not find.
Half of the spectrum.
I guess that. So we should look what this.
So the distribution from pre-space tells you that the peak is at -1, and then half of them are fun.
Yeah.
Right.
So I think that we are going to look what's going on in this space here. So if we can find a real parameter region where we would have. So what we see now is that the scatterings still need to occur in Klein-Shin regime, so the peak is due to the synchrotron, but we need some inverse Compton component in order to modify the low energy portion of the spectrum.
Further comments?
So to add a comment, so you're right, I mean, this mechanism can help to populate the path of the alpha distribution between -1.5 and -1, but still, I mean, if you have a -2.7, then you have to do something else. Maybe some positions could be also in circulating regime, but only have one efficiency. Of course, we have also to keep in mind that for the limits of this distribution, there could also be effects related to the instrument which you measure this alpha. So I don't know if you have really to believe all the most extreme alpha values.
Yeah, we will have to see what GBM also tells.
Yeah, exactly.
Any other questions? Okay, let's thank all speakers.